Good day and welcome to Math 111H Calculus 1 Honors, The Joys of X. Today we'll discuss optimization. Now that you've studied how to find maxima and minima of functions, let's use this concept to solve problems asking us to maximize or minimize quantities. For example, suppose you want to create a rectangular yard adjacent to a long straight wall and you have 300 feet of fence. What should be the dimensions of the yard in order to maximize the area of the yard? That's an example of a problem where we want to maximize something. We want to maximize the area. Here are the steps that we go through in solving optimization problems. First, you need to read the problem carefully and make sure that you understand what is being asked for and what the situation is. Sometimes it's helpful to draw pictures because often they'll help you to visualize the situation. Then it's important to assign variables to the quantities that are relevant in the problem and write an equation relating the variables and relating them to whatever it is that needs to be optimized. We need to understand which variable needs to be optimized, and then using the equation and using calculus, we can solve the problem to find a maximum or a minimum. And then finally, we need to consider the solution that we get and ask ourselves whether the solution is reasonable. Let's go back to our example. Suppose you want to create a rectangular yard adjacent to a long straight wall and you have 300 feet of fence. What should be the dimensions of the yard in order to maximize the area of the yard? So we have a long straight wall. We have 300 feet of fence with which we're going to make a rectangular yard. So I used X to represent the length of fence perpendicular to the yard. Okay, I have two of those, and we'll use Y to represent the length of fence parallel to the yard. Okay, so first we read the problem, we drew a picture with a wall and a rectangular fence, and we assigned our variables X and Y to denote what we feel will be important physical quantities, these two lengths. The area of the yard, therefore, is going to be X times Y. What do we need to optimize? Well, we need to optimize the area, so we'll let A of X and Y equal X times Y. So then we need to solve to find a maximum, but in order to find a maximum, we need to take a derivative. We need to find where the derivative is 0 or where it doesn't exist. And however, in order to do that, we need an equation in one variable. So in order to deal with that, we need to express X and Y, find the relationship between X and Y. Constraint on X and Y that will help us find one in terms of the other. We have two regions of length X and one region of length Y, and the total length of fence that we have is 300 feet of fence. Now, we could say, well, maybe I could maximize the yard with less than 300 feet of fence, but we can always make the yard larger if we have more fence. We could always add to either X or Y if we had more fence. So we know we're going to have to use all of the fence in this case. Then we can solve for Y. That gives us Y equals 300 minus 2X. We plug in A of X and Y is X times Y. So then we get A of X is X times 300 minus 2X. Now let's solve. Well, we write A of X is X times 300 minus 2X. We'll simplify 300X minus 2X squared. We'll take the derivative, A prime of X, to find 300 minus 4X. And we know that we can find a maximum or a minimum where the derivative is 0. So we set the derivative to 0, which implies that 300 minus 4X is 0. 4X equals 300. X is equal to 75. And Y from before was Y is 300 minus 2X. That's 300 minus 150 is 150 feet. So X is 75 feet. Y is 150 feet. We also need to check our endpoints. Now, we know that X must be at least 0, and our equation was in the form of A of X. So we could see if there are certain limits that constrain X. X must be at least 0 feet. If it's less than 0, it wouldn't make sense. And X could be no longer than 150 feet because we go up X and then we come down X in terms of fence use. And so we would have 150 feet up, 150 feet down in order to make 300 feet. So we know that x has to be at least 100 feet, but no more than 150 feet. We can plug in a of 0 gives us 0, a of 150 gives us 0 as well, a of 75 when x is 75 and y was 150, we get 75 times 150 is 11,250 square feet. These are our candidates for the maximum area, and it's obvious that the maximum area must therefore be 11,250 square feet. So we should make the portion perpendicular to the wall 75 feet long and the portion parallel to the wall 150 feet long for an area of 11,250 square feet. So let's just review. When we have an optimization problem, it's important to read the problem carefully. Often we'll find it useful to draw a figure. We assign variables, write an equation or more than one equation relating relevant quantities. In our case, we had an equation for area, and then we needed another equation to relate x and y so that we could write our equation for area in terms of just one variable. We have to understand which variable needs to be optimized. Then we use calculus. We take the derivative, set it to 0, find where the derivative is 0 or where the derivative doesn't exist, and we also check endpoints, and then we consider whether our solution is reasonable. Did we get a negative area, for instance? Okay. A mathematician, a physicist, and an engineer were traveling through Scotland when they saw a black sheep through the window of the train that they were traveling on. "Aha," says the engineer. "I see that Scottish sheep are black." Says the physicist. "What you really mean to say is that some Scottish sheep are black." "No, no, no," says the mathematician. "You two are so imprecise. Really, all we know is that there exists one sheep in Scotland which is black on one side." Thank you for joining us today. Have a great day, and may the power of math be with you.